Module 4, Investigation 5, In-Unit Growth and Decay Factors. For exercises 1 through 2, determine specified growth or decay factor, percent change, and initial value for each of the following exponential functions. Number 1, f of x equals 9.5 times 1.24 raised to x. Okay. So, first thing to notice here is that the 1.24 is the 1 unit growth factor because we have and just an x up here, so we're inputting x. For each 1 unit increase in x, we multiply the value by 1.24. So that 1.24, it's really important, that's the 1 unit growth factor. Now for the half unit growth factor, well, a half is half of 1, so we're going to need to multiply 2 of the 1/2 unit growth factors together to get a 1 unit growth factor. Since this is in part A, I'm just going to say that the 1/2 unit growth factor is A, so we know that A times A will equal the 1 unit growth factor, which is 1.24. That means A squared is 1.24, and so A is the square root of 1.24, otherwise known as 1.24 with an exponent of 1/2. Notice that this is because 1.24 to the 1/2 times 1.24 to the 1/2. If we multiply those together, we get a whole 1.24. Anyways, this answer is 1.14. And I have now run out of room, so I'll just put that answer over here. Now for the 2 unit growth factor. Well, to find the 2 unit growth factor, we know the 1 unit growth factor. So the 2 unit growth factor will actually be the 1 unit growth factor squared. 1.24 times itself will give us the 2 unit growth factor. And that's 1.5376. Okay, now the 2 unit percent change, finally something easy. It's just this decimal right here, 0.5376, or 53.76%, and that's an increase. Now we could have again done that by taking the growth factor and subtracting 1. Okay, now the initial value, oh great, another easy question is 9.5, because this is just the standard exponential form, the initial value times the growth factor and your units, your input. Okay, now our new function, number 2, g of x is 0.46.874 for x. That's pretty interesting, with a 4x there. What that tells. Okay, so let's think more about what this means for a second. I'm going to rewrite the function a different way. This is 0.46, and then using my laws of exponents, I can rewrite this as 0.874 to the 4th raised to the x. Now notice that my input is x, just like in the first one now. So I know what my 1 unit decay factor is. It's 0.874 to the fourth. And we could plug that into the calculator and get some answer. But now that helps us with the 1/4 unit decay factor. What's the factor that we multiply by itself 4 times to get 0.87 to the fourth? It's just 0.874. Then the 5 unit percent change. Well, first we would have to find the 5 unit decay factor. And so the factor, we'd take the 1 unit decay factor and multiply it by itself 5 times, which just means we raise it to the 5th power, which is 0.874 to the 20th. Again, from our rules of exponents, 4 times 5 is 20. So here I get 0.58. Okay, now we get 0.068. So then the percent change is just the factor minus 1. 0.068 minus 1 is negative 0.932, or negative 93.2%. So there's a pretty substantial 5 unit percent change. And by the way, this number was 0.5835. And the initial value 0.46. Just plug 0 into this function and we'll see here's our initial value. Well, that was fun. In exercises number 3 through 4, determine the specified growth or decay factor, percent change, initial value, and function for each of the following tables modeled by exponential functions. So just taking a look here, right away I see my initial value is 16. It's kind of nice. Don't see anything else jumping out at me. I do see that the inputs are increasing by 2. So we can find the 2 unit decay factor. If we call that A, 16 multiplied by A, our 2 unit decay factor, should give us 10.24. Or A is just 10.24 divided by 16. And I get 0.64. There's the 2 unit decay factor. Now, if we want the 1 unit percent change, we're going to have to find the 1 unit decay factor. So off to the side, the 1 unit factor. If 2 units is 0.64, the 1 unit will just be the square root of 0.64, or 0.64 to the 1/2, because we need 2 of these multiplied together to get the 2 unit decay factor. And that is 0.8. That tells me the 1 unit percent change is negative 20%. How did I get that? 0.8 minus 1. Really, I just look at 0.8 and I know that if that's our decay factor, we're decreasing by that factor, then the percent decrease will be 20%. Okay, the 3 unit decay factor, that's just going to be the 1 unit decay factor, which was 0.8, and it's multiplied by itself 3 times, so 0.8 cubed, which is 0.512. Now to find the 1/2 unit decay factor, I'm just going to take the square root of the 1 unit decay factor, because we'll multiply by 2 of these, square root of 0.8 times square root of 0.8, to get the whole 1 unit factor. And again, you could raise that to the 1/2 power, 0.894. And our initial value we got was 16. Now our function, let's just call this function f of x. Oh, it's already given us that name up here in the table. Now this is just a standard exponential function with our initial value of 16, and let's use our 1 unit decay factor, which is 0.8 to the x. Now there's other ways that you could have written this one. You could have used the other decay factors, like you could have wrote f of x equals 16, and then if you use the 2 unit decay factor, 0.64, you could take your x and divide it by 2. Anyways, number 4, we have another nice looking table. Notice that here the inputs are all increasing by 3, so we can find the 3 unit growth factor. 260 multiplied by the 3 unit growth factor will equal 278.2, and 278.2 divided by 260, that's 1.07. There's our 3 unit growth factor. Now if I want my 6 unit percent change, well, first I have to find the 6 unit growth factor. Now we could just take that 3 unit growth factor and multiply it by itself, or square it, and that'll give us the 6 unit growth factor. So 1.07 squared is 1.1449, and so my percent change is the decimal part, that 0.1449, or 14.49%. Let's do this another way. First, let's find the 1 unit growth factor, which we can find it by taking the cube root of 1.07, or 1.07 to the 1/3. And I get 1.023. And going back to part B for a second, if I take 1.023 and I raise it to the 6th power, I get 1.14. Let me actually do something different. I'm going to take my exact answer and raise it to the 6th power so these numbers match up. Get 1.1449. The numbers will be a little bit off if you round to 1.023, but notice that's the same thing that we got here almost, except it's the percent change, so we just need that decimal part. Then the 1/4 unit growth factor, that's just going to be the 4th root of the 1 unit growth factor. Which is about 1.0057. Let's see, our initial value. Well, I don't know what the initial value is, but I know if I take my initial value, let's call it I, and I multiplied by the 1 unit growth factor, I'd get 260. So I times our 1 unit growth factor, 1.023, would give us 260. So I is 260 divided by 1.023, and I get 254. So now we clearly have our function g of x. It's our initial value, 254, with our 1 unit growth factor, 1.023, and our input x as the exponent. These sure are fun. Seriously, it's pretty cool. In exercises number 5 through 6, determine the specified growth or decay factor, percent change, initial value, and function formula for the exponential function with the given graph. Number 5, use the graph below to determine the following values. Part A, the 2-unit growth factor. Okay, so good thing that they've increased the input by 2 units from -1 to 1. There's 2 units here as our input. So we can find the 2-unit growth factor. So let's call that 2-unit growth factor A. We know that if we have the value, this is 15.625, and we multiply it by our growth factor, our 2-unit growth factor, we get the output that's 2 units away, 40. And that, of course, means that A is 40 divided by 15.625. .56. Now the 6-unit growth factor, notice that 6 is just 2 times 3. All we have to do is take 2.56 and multiply it by itself 3 times, or cube it, and we get 16.78. It's pretty cool. You could have found the 1-unit growth factor and by taking the square root of this number and then taking that to the 6th power. That would have given you the same thing, which we do now have to find the 1-unit growth factor in order to find the 1-unit percent change. But like we've already mentioned, that's just the square root of the 2-unit growth factor. Uh, 2.56 to the 1/2 is 1.6. Now that's, I'm just going to label that here 1-unit growth factor, because that could be pretty useful. And so our percent change is 60%, 1.6 minus 1. The 1/2-unit growth or decay factor, we can just take the square root of the 1-unit growth factor, and we get 1.26. Or 1.265 is a little bit more precise. The 3-unit growth factor, that's just the 1-unit growth factor cubed. 4.096. The initial value, it looks like it's about 25 or something, but we can find it because we have the 1-unit growth factor, and we can just take, say, the 15.625, that output, multiply it by our 1-unit growth factor, which is 1.6, and that'll tell us the value 1 unit ahead, the output there. And that's 25. And so our function, I'm just going to call it f of x. It's equal to our initial value, 25, times the 1-unit growth factor, and our input is the exponent. Okay, use the graph below to determine the following values. The 3-unit growth factor, so notice that when we increase here from this point to this point, the change in input is 3. So if we take our initial value, 60, and we multiply it by the growth factor, we'll call it A, we're going to get 36.8475. And so our growth factor is 36.8475 divided by 60. That's about 0.614. There's our 3-unit growth factor. 6-unit growth factor, well, we just need to square 0.614. And we get about 0.377. Then we need the 1-unit percent change, so first let's find that 1-unit growth factor. And to do that, we can just take our 3-unit growth factor and find the cube root. And that's 0.85. So our 1-unit percent change, this is a decay, it's negative 15%. You could have found that by 0.85 minus 1, the growth factor minus 1. Now the 1/2 unit growth, or actually, yeah, these are all decay factors because we're decreasing here. We simply take the 1-unit growth factor, 0.85, and take its square root. Which is 0.922. Then the 5-unit decay factor, we just take our 1-unit decay factor and we raise it to the 5th. Which is 0.444. Okay, here we can clearly see on the graph our initial value is 60. And so our function, we could call it f, our input x is 60, and our 1-unit growth factor with our input x. In exercises 7 through 9, determine the growth or decay factor, percent change, initial value, and function for each exponential situation. So 7, an investment of 6,300 increases by 7.3% each year. Okay, so what do we have here? First of all, we have the 7.3% increase. That's our percent change, our 1 year percent change. So I want the 1-unit growth factor. That would be pretty useful to know. And that's going to be equal to 1 plus the percent change, 1 plus the percent change as a decimal, 0.073. So 1.073. So that means my 2-year growth factor is 1.073 squared, which is 1.151. Okay, now if I want my 1/2 year percent change, I need my 1/2 year growth factor. So my 1/2 year growth factor is the 1-unit growth factor. 1 year, that's my units or years here. 1.073, and I'm going to need to take a square root. And we get 1.036, and you see the percent change there is the 3.6%. My initial value, my investment was $6,300, so here we have our function is the initial value, 6,300, my 1-year growth rate, 1.073, and then my input x will be the number of years elapsed. Number 8, after having 1.97 million people in 2010, the population of a city has been decreasing by 4.2% every 3 years. Okay, so this is our 3-year percent change. So that means the 3-year growth factor is equal to 1 plus, it's really a negative 0.042 because it's a decrease. That is 0.958. That's my 3-year growth factor. Sorry, it's a decay factor because we're decreasing. So if I want my 1-year decay factor, I simply take the cube root of that, and that's 0.986. Okay, then I want the quarter-year percent change, so I first need to find the quarter-year decay factor, which will just be the 1-year decay factor raised to the 4th. Which is 0.996 about. And so my percent change will be 0.996 minus 1. Negative 0.004. That's about negative 0.4%. Okay, my initial value, that's 1.97 million. Then my function, this output is going to be in millions of people because I'm just going to use 1.97 here, and my 1-year decay factor 0.986, and an x here for time. Number 9, the amount of caffeine in your body decreases by 27% every 4 hours. Okay, so the 4-hour decay factor would be, let's see, 1 minus 0.27, or 0.73. So that means the 24-hour decay factor would just be, let's see, we're going to need 6 of those 4-hour decay factors because 4 goes into 24 6 times. So 0.73 to the 6th power is 0.151. Now the percent change will be the growth factor minus 1. Negative 0.849 or 84.9, negative 84.9%. So an 84.9% decrease. Okay. So here we already have the 24-hour decay factor, which was 0.151. So the 1-hour decay factor, since there's 24 hours in 24 hours, will be 0.151 to the 1 over 24, which is 0.924. Then the 1-hour percent change will simply be 0.924 minus 1, which is negative 0.076 or negative 7.6%. So we have a 7.6% decrease in the amount of caffeine every hour.